Okay, so everyone, we'll come back to our discussion about signal and systems in electrical engineering. And last time we finished chapter 1, which is about the basic definitions and the properties of important signals and systems. And the homework 1 will be due on the homework 1, which is basically for chapter 1, due next week, which is September 20th. Okay, so today we will talk about another important topic in chapter 2, and in order to better prepare us for this, I'd like to just give a very brief review of what we have seen in chapter 1 and what we shall see in chapter 2. So, as everyone may have been aware that the subject of signal systems is to study a very general concept of system and the corresponding input-output relationship, of signals. Okay, so by signals here, it can be a very broad meaning term. It can be just a function that is indexed by, for example, time or other variables which represent some physical phenomenon. For example, you can say the temperature now is a signal. You can say one's annual income is another signal, something like that. And by system, I mean a process that tries to process the input signal and produce the output signal. And that's also a very broad term. And in chapter 1, we talk about two different types of settings. We talk about discrete time signals, which is denoted by something like this. You can say this is nothing but so we use a variable n as a time index, and we are only caring about signals at integer points. And we also talk about continuous time signals, where the signal is indexed by a real number, which is something between minus infinity and infinity. So examples of discrete time signals include, say, one person's annual income over years. And examples of continuous time signals are such as the current temperature or the song that you hear from me at this moment, something like that. And we talk about discrete time and continuous time signal, and also we will have discrete time systems, which is basically a system that take discrete time signals as input and output. And we'll also have counterparts in continuous time setting. So in a continuous time system, the system will take a continuous time input and output a continuous time signal.
What is the n in the?
The n is just a time index.
Okay.
It represents the time that you're referring to. Say, if you're talking about the annual income, it can be the year.
Okay.
Yeah.
Because you use different symbols.
Yeah. So the difference here is that the index in discrete time setting is always an integer.
Oh,
But in the continuous time, it can be any real number.
Oh.
Yeah, any questions so far? Okay, so we have this discrete time and continuous time signals and systems. And in chapter 1, we also talk about some representative signals and system properties. For example, we talk about important signals such as periodic signals which are signals that repeat themselves after a fixed amount of time. And we talk about spatial forms of signals such as sinusoidal signals or exponential signals. We also talk about two very special types of signals, which are the unit impulse signal and the unit step signal, which we will review immediately. And for systems, we also talk about some important system properties. For example, we talk about a system with or without memory. By saying a system has memory, we mean the system's output not only depends on the current input, but also depends on the past input. And we talk about if a system is invertible or not. If a system is invertible, then we can refer the output from the input, and we cannot otherwise if it is not an invertible system. And we also talk about some other concepts like a causal system, which basically means the current output only depends on the current input and the past input, not depend on the future input. And we also talk about stable system, which is a system that satisfies the bounded input, bounded output conditions. If the input is bounded, then you will always be guaranteed a bounded output. And we also talk about two very important concepts that we will also review right now. The time invariant property of a system and the linearity of a system. So, in order to prepare us for chapter 2, I will give a very quick review of three important elements: the unit impulse function, the time invariance, and the linearity. So, is that clear? I erased all this? So we define unit impulse function as a very special type of signal. Which is, if a signal is a unit impulse signal denoted by delta n, that means this signal is only 1 when your n is 0, and it's always 0 otherwise. And we have similar definition for continuous time, but for now, let's just focus on discrete time cases. So you can see this is a very special type of signal, and it is mainly useful for mathematical convenience, and we will see that very soon. And also we talk about two important properties about systems: the time invariance So we say a system is time invariant if the system's behavior is fixed over time. In other words, the output that you will get from a fixed input doesn't depend on a particular time. You can input the signal today or tomorrow, you will get the same output whatever the time is. And we'll also talk about linearity. So we say a system is linear if the superposition of input signal leads to the superposition of output signal. So these three things that we will use right now for chapter 2. Is there any questions so far? So the primary topic that we'll talk about today is linear time invariant system. Or we will generally refer to as LTI system for simplicity. The purpose of studying such systems primarily comes from a difficulty that we face when we try to characterize a system. So imagine this scenario. You are given a system which is viewed as a black box. And your task now is to provide input to this system and measure the output. You can do whatever this kind of input and get the output. And the goal here is try to predict the output if you are given a new arbitrary input. So for example, you can do any kind of input-output measurement. And when I give you a new input, like an arbitrary x of n, you must be able to tell me what will be the corresponding output. So you can think how this task is going to be achieved. So you can think actually in the most general case, in order to perfectly predict what the output will be, you have to try all possible input in advance and record the corresponding output. So that when any given input comes in, you know what the output can be. So you can imagine that this is very difficult in reality, if it is not impossible. Right? So we know such a complete or perfect characterization about the input-output relationship of a general system is very difficult. But in the case of linear and time invariant systems, this can be significantly simplified. So let's see how this is achieved. So let's say we are given an arbitrary signal, x of n. It can be something like, for example, an important trick for the LTI system to have a much easier characterization is to view an arbitrary signal, x of n, as a spatial superposition of multiple individual unique impulse signals. So if we are given such x of n, then basically we can say that this input signal x of n is nothing but the sum of all these kinds of impulses. So each of these individual impulses has only one peak at a certain point and zero otherwise. So for any arbitrary input signal, it can have this kind of decomposition. And anybody tells me how we can write this mathematically? Do we have any mathematical expression for this? You can say this is nothing but x of minus 1 when your n is minus 1. and 0 otherwise. Is this correct? Yeah. And using the unit impulse representation we just have reviewed, this is nothing but x of minus 1 delta n plus 1.
5 minutes.
Yeah, sure.
5 minutes.
5 minutes, okay. Yeah, so we can say this is just the equivalent representation of this single impulse. And so mathematically, now we can say that an arbitrary input signal can be returned as many terms in such a form. Or in other words, it can be returned as a simple summation. So this is an alternative representation of an arbitrary input signal. Now let's see how we can. So this is a very general system representation. So let's consider if we have a linear system. If we have a linear system, then for such a given input, what will be the output? We know if we look at this expression, we actually can see that this is nothing but a superposition of many of these delta functions of different time shifts. So if we are given a linear system, then we can say that the corresponding output of this system will also be the superposition of the output of this individual delta functions. So if we say delta of n minus k has an output which is h of k, then we can say the overall output of this system will be simply xk of So from here you can see that the problem of measuring the input-output correspondence has been simplified in the way that in the most general setting, you need to test all possible input and output to have a perfect characterization of the system. And now the only thing you need to do is to try different impulse functions of different time shifts. And by testing all such delta functions and you record the output, then you can predict the output of an arbitrary system by combining all these individual outputs. This is one step that simplifies the problem of characterizing a system. And now let's imagine what would happen if we have a not just linear, but a linear and time invariant system. So for a linear time invariant system, we know if our delta then corresponds to an output of h0, as we have written there, then what will be the output of delta n minus some n0 if we shift, let's say not n0 but some k, if we shift this delta function by a time k. We know if the system is time invariant, then when we shift our input, then the output will just be automatically shifted in time as well. This is because this system's behavior does not depend on the time. So if you shift your input, then you're basically just also shifting your output. So we know this delta of n minus k, the shifted version of the delta function, will lead to h0 of n minus k. In other words, the overall output that we will have here will be simply so earlier we have for each index value of k, we have a particular output hk of n. But now we only need one single such output, which is h0 of n. So this is nothing but the output of a very special function, input function, a delta function. And we call this function as the unit impulse response because this is the response of a system to a unit impulse function. And one can see that under such a setting, if our system is LTI, linear time invariant, then in order to have a perfect prediction of the output signal, the only thing we need to measure is only the output of this delta function. So the problem becomes much simpler. So that's why we are primarily interested in LTI systems for these purposes. And next, I will talk about more concrete examples that shows how we're gonna, for example, interpret this expression or how we can do some calculation using this and so on. Any questions?
Yeah, so in the right, so the linear system was expressed to hk, and in the left, it seems like it used another expression.
Which one?
The delta n minus k is.
Yeah. So the key thing here is, if the system is not time invariant, then every shift value of k, you will have a special form of output signal.
Okay.
They can be totally different. But if your system is not only linear but also time invariant, then when you shift your input signal, you will just have a shifted version of your output signal. So your output signal are not totally different at all. They are just shifted version of each other. So that's why you don't need, as here, to measure the output of individual input, individual shifts. So you only need to measure once the output of this delta function, and you can perfectly predict the system's output to an arbitrary input by combining all these outputs to the impulse function. Okay. Any more questions?